Welcome to lecture 45, which is on spatial filtering in digital image processing. This is one of the pre-processing techniques where we enhance the images prior to classification. So in this lecture you will learn what are the different types of filters and what is their role as far as the image enhancement or pre-processing of the image is concerned. So let's begin. When we are doing image enhancement, in fact, we are doing three kinds of operation. As you can see, we are doing the point based operation where pixel by pixel we read the image, transform it and create the output image. Then there is a local operation. In the local operation, we are taking a group of pixels. Normally we take a 3 by 3 window or 5 by 5 or 7 by 7 window and apply some kind of a mathematical equations within those pixels and replace it with the central pixel. The third operation is the global operation. The entire process we apply at once to the entire image. So you can see in the diagram below also. So this is pixel by pixel, this is a group of pixel and this is the local operation. So pixel by pixel transformations you have already learned in the previous lecture. So today we are going to learn the mainly the local operations, how we are taking a group of pixels, applying it and replacing it with the central value. So when we are doing this spatial filtering, we have the input image, and in the input image in the group of pixels, let us say this example is for 3 by 3 window, we take 9 pixels together and take the value of the central pixel, which is the x and y coordinates, and do some kind of a transformations with those 9 pixel values. So we have 9 pixel values, we can take the average, we can take the standard deviation of these values, we can select the maximum out of these 9 values or the minimum out of the 9 values and try to replace in the central pixel in the output image. So this is what we are doing, actually taking the help of the neighborhood pixels and applying the transformation equation and changing the characteristics of the central pixel. So we are creating a new value in the output image which may not be a part of the input data set. So mathematically we can actually show as gxy is equal to t multiplied by fxy, where fxy is input image in terms of the coordinate system x and y of a pixel, and t is some kind of a transformation equation and g is the output. So here when we are applying a window, a 3 by 3 window or 5 by 5 or 7 by 7 window, this is called applying the mask to the operations. When we are applying the transformation equation, it is also called templates, kernels, windows, mask. So there are different names which have been given in the different literature, but the basic idea and the basic principle behind that is same by selecting the window size. Now coming to the filters, when we do the filtering process, there are broadly two kind of filters which we normally use, low pass filter and the high pass filter. These low pass filters, they are also called the smoothing filters because they create a smoothing effect in the output image. So my output image is much more smoothing the features, the objects, and the second category is the sharpening filter or the high pass filters. So high pass filter will sharpen the objects, boundaries of the objects, the edges of the objects. So both have very important role to play when we are dealing with the remote sensing images and satellite remote sensing data. So we will learn both the filters in detail now. So if we look at the low pass filter, which is called the smoothing filter, they are also used for reducing the noise and eliminating the small details. So if individual pixels are there, with that noise, we remove that noise, or individual pixels with some different values, that is also removed. So many times when we are actually doing the classification, and after the classification we want to smoothen the image, we want to remove those individual pixels which could be unclassified pixels or which could be a noise in my data set, we apply smoothing filter. But in the raw data also sometimes the noise is present. So we are actually applying this with the different size of filter, and in this example the 7 by 7 Gaussian mask is shown, but here the elements of all that window for that mask will be all positive. So we have to select the elements in a 3 by 3 window, all 9 elements, they will be positive, and if you normalize the weight, it should be, the sum will be equal to 1. So that is how we design these low pass filters. So you can design the filters and can apply to the images. Now this is the effect of the smoothened image. This is my input data where we can see a mountain, hilly area, and in the smoothened image, after applying that filter, the image has become more soothing type of image. So if we see the further classification of these filters, these are averaging filters, these are called Gaussian filter, a median filter, the mode filters, they come all under the smoothing filter effect. So there are various kinds of filters which are available under the smoothing filter in the literature, but here in this lecture we will cover only the most popular one which are very frequently used by different authors. So averaging, as the name itself is suggesting, here in the averaging we are taking the average of all the values. So we are taking the filter which is as you can see here, all the elements are 1 and they are multiplied by 1 by 9, because when we are adding the 9 elements we have to divide by 9 in order to normalize the values. In case of a 5 by 5 filter, averaging filter, all the elements are 1, equal weightage to all the elements is given, and it is again multiplied by 1 by 25. In case of 7 by 7, it is 1 by 49, multiplied all the values. So designing the filter is very easy, but many of the image processing software now they have their inbuilt capabilities. But in case you have to write your own program, and then these elements are to be designed by the user. So the weightage is equal 1 1 1, and then you are dividing by the total number of pixel in order to normalize the value, so that the output value is not greater than, let us say in 8-bit image it is not greater than 255. So we have to take care of the output value. So this is a mean filter, or what we call as the average filter also. Both the names we called it, they will tend to blur the image. So slightly smoothing effect, blurring effect you will get. The image would look like very soft touch image, and many times we have seen this image of the landscape in the movies also, then suddenly this becomes very soft and smoothing. So there also low pass filters are applied to the image. Then this is the example of a 3 by 3 window, because most of the time we are applying 3 by 3 window, unless and until there is a specific objective and the object is also very bigger in the size normally, but we take 3 by 3 window traditionally. So all the elements are 1 and it is divided, the mean value is divided by 9. Now you can see in this animated image also that we have the input image where origin is at the top left hand corner, and we have the x direction and the y direction. This is my input image, and I will take the let us say the central pixels of the input image, and this is a 3 by 3 window. So I have superimposed what I see in the background here is all the digital numbers. So DN values of the image, they are shown like 104, 100, 108, 99, 106, 98, 95, 90 and 85. So they are all DN values within that 3 by 3 image and my window, my pixel will be all 1. So, if I enlarge this 3 by 3 window, you can see the read the pixel values in that 3 by 3 window, and if I take my elements now, because I am integrating these two together, my window and 3 by 3 window and the image. So, my elements are all 1 by 9. So, this is average filter which I am applying to all the data. So, this is like multiplication of the two. So, the first element of the dn value, here I am multiplying by 1 by 9 and then adding the second element multiplying by the second element of the window, and you can see more clearly in the expression below. So, what we are doing is 106, for example, we are multiplying by 1 by 9, 104 we are multiplying, which is the first pixel, then 100 is multiplied, then 108 is multiplied, 99, 98, 95, 90 and 85. So, one by one each pixel is picked up, multiplied by the corresponding filter values. The filter value is 1 by 9. So, I am adding these two together, all 9 values together, and when we are adding all the 9 together, I may get some real value. But the dn value is always an integer value, so we have to round off it. So, my output is 98. It means now 106, which was the my central value, has to be replaced by 98. Now, many filters will have some kind of a threshold also. So, if you are very close to the input value, maybe the value remains unchanged, but if it is beyond a threshold value, then you have to change it. So, the threshold can also be applied in order to consider whether the central value is required to be changed or not. So this is one window, but similarly for the entire line by line and pixel by pixel, this kind of analysis is repeated for the entire data set. So, this particular window remains common for entire data set, and the window moves line by line and pixel by pixel. So, you can see here that process we are repeating for the entire image, and we are creating one new output image with the new values. So, output image, for example, here the new value is 98. 98 is not present in the central value, which is 106. So, you have altogether a new values are produced, and sometimes we feel that this kind of processing when we are doing, when we are applying the mean filter image, the mean filter image has removed the some kind of a noise, smoothened the data, and this is much better than the original data. So, this is my original image, as you can see here, and in the original image a 3 by 3 filter has been applied, and this is what we are getting the output after applying the filter to the entire image. So, this is in terms of the noise removal, this is a much better. Now, what will be the effect if I change the size of the filter, if I go for from 3 by 3 to 5 by 5 or 7 by 7 or maybe much bigger 15 by 15 or 25 25 pixel size. So, this is what is shown in this experiment here, that this is my original image, and different filters 3 by 3, 5 by 5, 7 by 7, 15 by 15, 25 by 25. So, different filter sizes have been applied. Now, it is not necessary that I increase the size of the filter, I get better and better image at the end, not necessary, and this is what is shown here. So, I am getting good results from 3 by 3 filter. 5 by 5 also to certain extent is giving me satisfactory results, but the image becomes quite blurred if I select the bigger size of the window. So, it really depends upon the what kind of objects are present in the data set. So, we have to carefully select the size of the window when we are applying this smoothing filter. The second category in this is a median filter. This is a non-linear kind of a filter, and what we are doing is that in a 3 by 3 window or 5 by 5 window, all the values would be arranged in a certain order. So, if we arrange them in increasing or the decreasing order and take the central pixel value, right. So, that sorted pixel value is replaced by the middle value. So, if we arrange, let us say in 3 by 3 window, all the 9 values in ascending or the descending order, and take the middle value, uh, which is the fifth value when we are arranging in a row. So, that value is replaced by the central pixel value. So, here also we can change the window size also. So, but this example is for 3 by 3 window. So, in this 3 by 3 window, dn values are shown, but you can see that 20 is repeated several times here. Okay, and when you are arranging the values, you can see the middle value is 20 here, and that 20 is replaced by the output image. So, that is how you can create the median values also. Now, see the effect of the median values. So, this is the original image, and if I actually introduce some kind of a noise in the data, so the second image is that some noise has been introduced in the data set. So, this becomes kind of a salt and pepper look image. So, you can see either the white spots or the dark spots in the data, and there is no clarity also of the details as you can see in the original data. But to the second image, which is salt and pepper look image, now I am applying two filters just to compare them together and see which one is performing better. So, a 3 by 3 filter, averaging filter has been applied, and a 3 by 3 median filter has been applied to the second image here, and we find that the median filter image is much better in terms of the clarity of the details which were present in the. So, it is a median filter image is almost comparable to the original data. So, we find that median filter sometimes gives good results as compared to the average filter, and the reason is that the median filter will retain its original value. That means that the value which is replaced is a part of the data set. A new value has not been created, but while you are taking the average of 9 values, a new values might be created. So, you get altogether a different set of values in that case, but here in the median filter you are the part of the data set only. So, another example which shows that there is a image of the butterfly, and the salt and pepper look. So, that means some noise is present in my data set, but when you are applying a 3 by 3 filter, the image becomes quite clear from those isolated pixels and the noise. So, now this kind of image is preferred when we want to further carry out some kind of a analysis or identification of the objects. Another example of the median filter, it is also called the denoising filter, and the reason is that all the noise which could be present due to the malfunctioning of the sensor could be removed from the data set. So, here this is the output from the median filter. So, it has all removed the noise which are present in my original data. So, the third one is the mode filter. So, under this smoothing category, this is the mode filter, and again we will actually take the 3 by 3 or 5 by 5 or bigger window and arrange the values actually, and we will see which is the most repeating values in out of the 9 values. So, this is also acting as a noise removing filter. Okay, so it comes under the category of the noise removing filter. Now, example is shown that how you design a mode filter and how you calculate or pick the central value. So, suppose there are values 23, 25, 34, 23, 76, 58, 23, 45, 23. So, these are 9 values in a 3 by 3 window. So, we have the 9 values which are taken in the first row, the second row and the third row. Now, out of these 9 values, you will find that 23 is repeating in this particular lot 3 times. So, when 23 is repeating 3 times and my central value was 76, so I am replacing this 76 by 23. So, in the mode filter, what we are assuming basically that the central pixel belongs to the similar kind of a classes as the neighborhood. So, there is a similarity between the central pixels and the neighborhood pixel. So in the neighborhood pixels, which are the dn values, in majority like to pick that value and try to replace. So this is the design of the mode filter. So now you can see the left image has lot of noise which is present in the data set, and the mode filter has tried to remove the noise. Now the best thing of these filters are that you can apply these filters more than once. So if you feel that there is still some noise left, you apply them twice, you apply them thrice. So you can apply them a number of times till the successful image is obtained at the end. Now a comparison of the images, low pass filter images. So in the first column we see the results of the mean filter, results of the median filter. In the second column, the third column shows the results of the mode filter, and these are actually the first line is indicating 3 by 3 filter, second line is indicating if I apply the 5 by 5 filter, increase the size of the filter, the third one is 7 by 7, and last is 9 by 9 filter. So what will be the impact on my result, on my output, if I change the size of the window, and which one is the better, which one is providing me the better output. This is a comparison which has been shown from these three low pass filters, mean, median and mode. But again, it would depend upon the type of feature, the size of the feature, the orientation of the features which are present on the satellite image. Then under the smoothing filter we have the Gaussian filter. So it will follow the normal distribution. This is the 7 by 7 Gaussian mask which has been actually created. So here you can see the different weights are given to the different pixels. It is not the equal weight, we have given more weight to the central pixels and then slightly lesser weight to immediate surrounding pixels and like that, and as the distance increases the weight decreases. So we are applying some kind of a sigma threshold also, at what sigma level we will like to have the value. So these are the different sigma levels. So mu is the mean, then this is mu plus the standard deviation. So we take mean value and the standard deviation value, and we take mean plus 2 times of standard deviation and mean plus 3 times of standard deviation. So we will like to confine, let us say mean plus minus the standard deviation. Then what you see is the pink. So these are the values which you are considering in your data set. If you increase it the mean plus minus 2 sigma, then you are including the values which are shown in the blue region also. So this kind of a filter is also very good when you are talking about the smoothing of the data. So top image is the original data, and then you are applying that filters with the different sigma values, and you can see the impact of that. Very strong smoothing has been done in the second case. Then the second category of filters are sharpening filter. They are also called high pass filter. Very useful in image processing work, not only for satellite image processing, but outside the domain of remote sensing, these sharpening filters are being used. So they again have 3 by 3 or 5 by 5 or 7 by 7 window. Now you can have the positive coefficients and the negative coefficients. So it's not like all the coefficients should be positive like the low pass filter, but you can have positive and negative both, and they are enhancing the image by sharpening the features or edges. And there are several types of filters under the sharpening filter. High pass filter, the gradient filter, a first derivative of the gradient, the Laplacian which take the second derivative, and then the difference filter. So they all are falling under the sharpening filters. So they will highlight the details, and elements could be, as I told you, positive and negative, but the essential condition here is that sum of all the elements should be equal to 0. So weighted sum was 1 in the previous case, but here it is equal to 0. As you can see in the 3 by 3 element, the first row all the elements are minus 1. Then in the second row the middle element is 8 and all other elements are minus 1, and the third row is all the elements are minus 1. So if I add them up together, all the elements, so in the periphery I have all minus 1, in the center I have 8, so sum will be equal to 0. So this is the kind of a principle which we have to use, philosophy which we have to use while we are designing the sharpening filter, that sum should be equal to 0. Now by subtracting a low pass filter image from the original image, a sharp pass filter is obtained. So it is just opposite in nature to the low pass filter. So if I have the original image data and I have the low pass filtered image, if I subtract the two together, because images are like a matrix, so you can subtract the two images, you can add the two images, you can multiply, you can divide, like you do with the matrix value. So same thing here we are also doing. We have two images with us, we are subtracting pixel by pixel subtraction, and we are creating a new image, and we can get the high pass filtered image. So here you can see that result of the sharpening filter, this is my input data and the sharpened image. So one can see the craters on the moons also very clearly. So some of the features which were not very clearly seen on the original data, input data, but after applying the sharpening filter, these are now very well seen on the sharpened image. Now under this sharpening filter we have the first derivative of the, where we are taking the gradient slope in the x direction and in the y direction. So we are creating the image derivatives using the gradient formula, and we know we have a 3 by 3 window. So one direction is x, another direction is y. So we calculate the gradient vector. Now we know the vector has a certain magnitude and vector has a certain direction. So when we are talking of the vector, then magnitude and direction we can calculate with the help of the well known relationship. Now here we have the first derivative in x direction and y direction. So magnitude will be delta f square upon delta x plus delta f square upon delta y. If I add them together and take the square root of that, then this becomes the magnitude. Now if we add the two values together also, then we found that there is not much change, they are very close to each other. So normally sometimes we are simply adding up delta f by delta x plus delta f by delta y. Now the direction, we know the gradient direction is tan inverse delta f upon delta y divided by delta f upon delta x, standard relationship which we are using in mathematics also. So we calculate the magnitude as well as the gradient, and we can highlight certain features in the different directions which are there. So here is a mask which is a 3 by 3 mask, and Z1 and to Z9 are the elements, and they have been selected in such a way, these elements, that if I take the sum of that becomes 0, and now if I calculate from Z1 to Z9 elements which are taken from the image, dn values from the image, I can calculate the gradient in the x direction, which is Z8 minus we take Z5, and it is Z6 minus Z5 data. So we are taking the difference of that values and then calculating delta f by delta x and delta f by delta y. So you can see that this is the original data set, and in the original data set now I am applying the gradient in the x direction and gradient in the y direction. So one is this output and another is that output. Now I can add these images together in order to highlight the x direction and y directional features. So there are many features which are oriented towards x direction, there are many features which are oriented towards y, but there are other features which are oriented in the other directions, which could be the diagonal directions. So in order to do that, I am applying different filters and I can add these two together for getting the better results. So these gradient filters, Previtt and Sobel, they are the other operators, other filters under the uh, edge detection filter, so which can actually give me the edges very well. And again, if you see the elements of the Previtt operator, that horizontal all is -1, then second row is 0 and the third is all +1. So if I add them up together, this becomes the sum becomes the 0, and this is very useful kind of a filter for horizontal edges extraction. So if suppose there is a road is a linear feature, or some features which are oriented towards the horizontal direction, we can highlight those features. The second filter is just the reverse of that. The rows are shown into the columns, right. So now the first column is all -1, the second column is 0, and the third column is all +1 here, sum is 0. So I apply this particular filter, now it will extract the vertical edges. So if I take the gradient of the two together, then I can highlight all the. Similar in nature, the Sobol filter is there. It is a gradient filter. Sobol has designed a filter. So here in place of -1 we have -2. So you can see that in place of -1 we have -2, in place of 1 here we have the 2. So again the sum is equal to 0, but this filter also has been found to perform sometimes better than the Previtt filter. So the Sobol filter, the Robert filter, Previtt filter, they are the filters which are used under the gradient. So these are shown actually here now. These are the different filters, and one will highlight the horizontal line, the another will highlight the vertical lines. And so again, if I come back to the same data, this is the image which is highlighted in the y direction, this is the image which is highlighted in the x direction, and these are the edges in all the direction, because we have taken the gradient magnitude of that. So images, now one can see the edges, boundaries very sharp. So all those white lines what you see is the edges of the object. So one can actually identify the shape of the object, the orientation of the object, and then this data could also be converted into the vectored format. So second derivative gradient are also the Laplacian filter. So these are very popular filter, and mathematically I have shown in this we are actually multiplying the two here together and taking the second derivative of the data, and these are the filter designed. So you can see here the middle value is 1, -2 and 1 in one case, and then in the column it is 1, -2 and 1. So here also again the sum is equal to 0, and we are applying this kind of a filter to get the results. So if I just show you the results of the image, original image here, and then I have the Laplacian filter and the Sobel filter results. So I can see the Sobel filter is giving me better and better data as far as the details, the minor details are concerned. I can get the good edges in the data set. So this is the again another results of the Laplacian filter. We have the original image, then Laplacian filter image, and then this is the contrast enhancement which you have learned in the first earlier lesson of the image processing. Edge detection, we can detect the edge of any structure also. As the example you can see the edges of the buildings have been extracted from this kind of a filter, and one can carry out the measurement and can also create a vector map out of this data. So this edge detection filters have been used also to for identification of the photographs also. Then in medical science, you can see this is the MRI scan of the kidney hurt on the left side, and right side is all those boundaries of the small features. So one can find out if there is some object size is bigger than the normal size. So one can identify the actual cause of that. So these spatial filter, the summary is that there are broadly two kind of filters. They are enhancing the details of the image, and they are very much necessary for identification of the features from the data, or if we have to carry out some measurements, or we have to create a vector image for GIS work. So it has a lot of application as far as the image processing is concerned, or forensic science or the medical science. So this is all about the filtering chapter. Thank you.